In this exercise, we're going to go ahead and design a steel joist. If you go into any Walmart, Target, or any gymnasium, any area has a big span with no column, look up in ceiling, you're going to see these steel joist bar. It is commonly used, and a lot of structural engineer loves them. And because it's really easy to design, you just go to the load table. As long as you have the loads, you can go ahead and pick out the size. And but before we do that, let's take a look at the PowerPoint. I want to explain some stuff. This manual right here, and if you go to the manufacturer website, they have this manual there, or you can download this on Google, and they have a table, specified weight table for each series. They have K series, LH series, and DLH series. This is the picture right here. Look at the picture up here. And if you go to Walmart or any other large places, look up, you can see these steel joists. Let me go to the PowerPoint and tell you the classification. What they are, they come in this three classification. When you look at the K series, they designed for lighter load, and like a usually common roof in Walmart. And they can be anywhere from 10 to 30 inch deep, and they span up to 60 feet. That's pretty good, actually. Then you have the LH series, and they are capable of supporting heavier load. Their depth is about 18 to 48 inches and can span up to 96 feet. Then you have a DLH series, and these are heavy-duty one. They are anywhere from 50 to 120 inch deep. They can span up to whopping 240 feet. And there are also CJ series, which are composite steel joists. And if you look at the K series, there are something else called KCJ. Let me go to this PowerPoint. Right here, they have a KCS series, which is part of K series. And these are the same thing, and go up to 1060 feet. We'll design one of these anyway, a couple of these. And take a look at some of these pictures so you can see it. And there's a good picture right here. These, they are right here. And then you gotta have a horizontal bridge in between them. So just like design of any beam. If you're a structural engineer, you know how to design a beam anyway. And it's just like any other beam. When we design these, we're gonna check for a design for bending. And because the length is so long, bending and normally control, and then we check for shear, check for deflection, and check for bearing. That's design of any type of beam. However, in these series, they have this table, and the table themselves has calculated deflection and all that stuff. You don't have to do it. You just need to come up with the load. Once you have the load, everything become pick up from the table. It makes it a lot easier. So the load table right here. And they use both design bases. They use allowable stress design and load resistant factor design. What else I gotta show you? There's a picture right here. You can right up there. And we just go over some of the... We're gonna do 3 examples. You really should watch the 3 examples to learn about this joist. Give you a clear picture of it. If you go into the table, in the manual, they have table both in load resistant factor design and allowable stress design. And for every different type of series of joists. This one is for K series. And the left column is always clear span. And then designated size for the K series joist is given on top. It goes from let me see, it goes from 10 to 22, 26 K12, 30 K12. Then it goes to matrix, then it goes to low resistance factor design. So when you look at these, and this is your clear span, and then on here you have 2 numbers, one in black and one in red. The black is the load that you calculate on top of your beam, and that load should be pound per foot. So this particular 28K6 a 27-foot span, it can support up to 550 pound per foot. The red number down underneath, it could be the same, it could be different, usually smaller. That basically represent the weight that you're going to use to calculate the deflection, and it will give you a deflection equal of L over 360. Example number one, we're just going to go ahead and work on these two numbers to see what they are, how we calculate deflection. Before we calculate the deflection, the deflection for this is given by this equation right here. And I had a note here, if I can find it. The deflection is 15% higher than deflection for normal beam. So if I was doing a W shape or a timber beam, I use the beam formula and calculate deflection. But when you're doing these, you multiply it by extra additional 15%. And the deflection equation is given right here. They made it really easy. I is equal 26.76 times WL cubed. W is that red number we were talking about. So let's go do this example. We're going to go ahead in the table, look at 24K7, which is 40 feet long. And I drag out a table right here at 40 feet. 24K7 is right here. And if you come down, the number we're looking for is right there with my cursor hiding it, is 253 red, black over 148 red. So let's go to the other board so we can do this. So the number we had was 253 over actually was red. 153, 148. And if I have a beam, these beams are designed to be uniform distributed load. If the load is different condition than this, then you cannot do it. You have to go to a special cases. We'll talk about that in a minute. So this is W. In this case, that will be 253 pound per foot. And this is how it's done. To calculate the moment inertia, and that equation was 26.767 times W times L cube times 10 by negative 6, which is equal 26.767, and W is right here, and that is 148 multiplied by L is span was 40 feet, so it's going to be 40 feet minus 0.33 and by power 3 and multiplied by 10 by negative 6, and that comes out to be 247 inch by power 4. Let's go back. I want to show you something on my beam formula. You've seen beam formula. It's in the steel book. Back of any book you can find these equations. And for uniform distributed load, the deflection is right here at the center, is 5WL by power 4 divided by 384 EI. We already have calculated I. Now the W is going to be that red number that we just went over. But this has to be multiplied by additional 15%. So let's go ahead and do this. deflection is equal 1.15 additional 15%, and that equation was 5 WL by power 4 divided by 384 EI, which comes out to be 115 times 5 times 148, this number right here, and let's divide that by 12 times L is 40 minus 0.33 by power 3. Well, let's multiply by 12 and then make it by power 4. Divided by times 12. So this whole thing right here by power 4. Divided by 384. E is a 29 million for steel. And I came out to be 247. This 12 right here is basically, this is a pound per foot right here. The unit that is pound per foot. So we take the foot away and that's gonna work out. So our delta comes out to be 1.32 inches. Now if we go ahead, calculate L over 360, and which is basically 40 minus 0.33 times 12 divided by 360, it comes out to the same number. That's what it is. So this is example number 1. Here, when we look at the load designation is if you have DDKT divided by 2I, 24 stand for the depth of the joist, and then K is the series number. It could be K or DLH or whatever, depending on what material you're using. And then you have this number is basically 250, something like, could be 300, could be 400. That designation is how many pound per foot. That's a load calculation you have. And the red number, which we talked about, is you use those for the calculation of deflection. So let's do this second example, example 2 right here, and we're going to calculate the total load per, you're going to use allowable stress design method, and our joists are about, they are 5 feet on center, and just do the A part, we have 20 pound per square foot dead load and a 30 pound per square foot live load, and then we have a 16 pound per square foot downward wind load. Let's find out how we can use the load table to design one of these joists. Create the load per ASCE load combination. I have multiple video on that if you want to go take a look at those. But I'm just going to go ahead and go through it. Load combination, and we're going to do this in allowable stress design, or you can do it in load resistance factor design too. Let's just stick with this one for now. The next example we work with load resistance factor design. So load combination number 1, it's going to be basically dead load plus live load, and our dead load was 20 pound plus 30 pound live load, that's equal 50. And load combination number 2, you can look up on the screen for allowable stress design. There are 7, 8 load different combination. So number 2, which is basically a 5A, is a dead load plus 0.6 live load. No, I lied. Wind load, dead load plus 0.6 W load, and that's equal 20 plus 0.6 times 16. That'll give me 29.6 pound per square foot. Pound per square foot, same thing. And we have one more combination, which is a 6A. We're going to call it 3A. So it's a dead load plus 0.75 live load plus 0.75 times 0.6 wind load. If I got that right, and so that equals 20 plus 0.75 times 30 plus 0.75 times 0.6 times 16. 49.7 pound per square foot. One more load combination we have, and that's 4 is 0.6 dead load plus 0.6 dead wind load, which is not going to make it anyway. 0.6 times 20 plus 0.6 times 16, and that will give me 21.6 pound per square foot. So if I look at all these load combination, obviously this one right here controls. Okay, this example, it said it was at 5 feet on center. What I mean, if I look from the top, look at the roof from the top, so these joist bars are going like here, 5 feet apart. So the turbo tree width is at 5 feet. And therefore, if I'm going to calculate that 50 pound, it's going to be, total load is going to be 50 pound times 5 feet, and that gives me 250. That's a 5. My student always complain about my 5. They don't like it. There we go. 250 pound per foot. So this is the load we're going to go ahead and use to find our size of our joist. So let's take a look at the table. From the table, we're going to use 24K 250 over 150 at 5 feet spacing. So if we look at the table, the 24 inches the depth of the beam, which is set by architecture, or depend, it's always set because of your utilities. And then you have 24, K4, K5, K6, it goes all the way to K12. And what we're looking for, our number was 250 over 150. So the top number is the one we're looking for. So anything that can support 250. However, we didn't say what was the span. So if you have the span, just say for example the span is 30 feet, and if it's 30 feet, this one will do right there because 331 will beat 250. And if the span is 35 feet, we have to go to next one, which is right here, 273 over 184. And that will be our beam to select. Okay, let's go to the next problem. We can get a little bit deeper. Okay, take a look at another example, this one. We're going to design a floor joist based on what we have right here. We have 250 pound dead load and a 750 pound life load. Those are concentrated load. And a uniform distributor load is, dead load is 60 pound per foot and the life load is 180 pound per foot. The previous example was all uniform distributor load. But when you end up with the special cases like this, let me go over the PowerPoint, talk about different options first. Section 2.4 of the manual, it says if you have there are 4 or 5 different options, and it might fit to your load scenario. Section option 1 is, which we've been doing, is if you have a uniform distributed load with a simply supported, then you can go to the load table and it simply select the size of your beam based on a span and based on a load. Then there's option number 2, and there's option number 3, and option number 4, which we're going to do example on this one. And if you have a scenario that it's not uniform distributed load, you have a concentrated load or other type of load, then we do it like the old ways. We calculate the maximum bending moment, and we check the shear, see if the things work. Here I'm going to calculate this. Let's call this load resistor factor design. This will be allowable stress design. So the number is going to be different, but based on what you have on a board, and we're going to go ahead and make an adjustment for both different design systems. First, we're going to use a load resistance factor design. Our PU is going to come out to be 1.2 times 250 plus 1.6 times 750, and that will give me 1,500 pounds. So this basically becomes 1,500. Then we have, let me change color for good luck here. And then we have WU, which kind of come out to be 1.2 times 60 plus 1.6 times 180. And that will give me a 360 pound per foot. Now, because we have this concentrated load, we're going to use the moment and shear table to size our beam. And this, so this become 360 right here. Going to calculate maximum bending moment, and if we look at the beam formula, take a look at it on the board, and we're going to use that, and that's going to be PA B divided by L plus WL squared divided by 8. So that's equal 1,500 times 8 times 32 divided by 40 plus 360 times 40 squared divided by 8. My MU come out to be 81,600 pound. If I multiply that by 12 divided by 1,000, and that will give me a kip inch, which become 979 kip inch, and that's what the table has. And let's calculate the reaction right here. So we have one reaction, nothing there, another reaction. So call this R1. Our R1, let's change color again for good luck here. R1 is equal WL divided by 2 for the uniform distributed load. And if you take a moment about here, take it over there, it's going to be a P time, let's call this distance B right here. So that's the distance B, which is equal 32, A, which is equal 8 feet, total distance is 40 feet. Okay, so P times 32, well, let's say B for now. B divided by L, and plug in, and that was 360 times 40 feet divided by 2 plus 1,500 times 32 divided by 40. And I got 8,400 pound. And R2, D2, I've been watching Disney too much. It's going to be summation FY is equal 0, right? So how we do that, it's going to be 8,400. That's positive, minus WL is 360 times 40, and minus 1,500. And that will give me 7,500. So our shear 1 and shear 2 became that. Now let's take this and take a look at the table. So when we come into this table in manual, again, I wish they had number in their table so you could reference to it. This is a load resistance factor design. Make sure you are either in load resistance factor design or Robert stress design. And here you have a joist designation, and we have the depth. The depth was set by architect or whoever, was 22 inches. And our moment we calculated, the one best fit is this one, 22K CS3 with the moment capacity 987 kip inch and a shear capacity 9900. And we will come back to it here. Also got to keep in mind that this right here has a moment inertia is given to you right there, which is kind of nice. And the stability for bridging is given at 40 feet at number 9. So let's continue back to the E3. It will basically control this. And your moment is 987, bigger than our moment. One thing about the moment, and my moment came out to 979. If you look at the different manual, they might come out smaller. I use the beam formula, and I use this. They might go ahead and do a shear moment diagram. Their moment might come out smaller. And if you're a structural engineer, do it this way. It's okay, it's a little bit bigger than the other one because you want to be really safe here. These days, the structural engineer being pushed and pushed to design more economical, closer, and it's all the structure, they're not good as they used to be. The code is going in the wrong way. They got to come back and put more stability into it. Anyway, so you can do the same thing with Robert stress design. Your load is going to be different. It's just going to add them all up, and you come up with the same result. Take a look at the manual and go over it and familiarize yourself. It's really easy, and everything is, you have the hardest part to come up with the load, and then everything is, the table right there shows you what you need to do, and of course you got to contact the manufacturer and makes it a lot easier. Hope this was helpful.